Okay, so we're continuing with the C34 January 16 paper. This would be on a UK paper on C3 because it's functions. The first part is pretty straightforward. Modulus function, any positive values stay the same. So this bit here will stay the same. But this bit gets reflected. Let's try again. This bit gets reflected in the x-axis like that. Don't forget to write the asymptote, because it does say here the exact coordinates of the points where the curve crosses some axis or meets the coordinate axes and the equation of any asymptotes. So this point is still the same, minus a third ln 4, 0. And the asymptote would, because it's reflected, because we've made that modulus, is 4. And this point here will be equal to 0, 3, because all these negative values here become positive. Pretty straightforward. 4 marks, 4 very easy and quick marks. Part B, 3 marks. It's a combination of transformations. First of all, it's a stretch vertically. Times 2. Then it's shifted upwards. By 6. Now none of this is actually going to, obviously the shape of it will look different if put on the same axis, but the basic idea is going to be the same. It's going to be a curve with an asymptote, a horizontal asymptote. Let's have a look at what happens to each individual point here, and the asymptote. The asymptote was at y equals minus 4, but then we're going to times that by 2, so that makes it y equals to minus 8. And then we're going to add 6, so that puts it to y equals to minus 2. So our asymptote is going to be at minus 2. Now, the point 0 minus 3, if we times it by 2, that will make the point 0, because the x coordinate's not going to change, it's just the y coordinate, that's minus 6. And then we add 6, so it's going through the origin. Okay, and this point here, you might wonder what I do with that point, but what happens is that actually doesn't cross the axes at any point, so I'm not going to bother with that. So we've got the curve going through the origin and having asymptote at minus 4. Now I will tidy that asymptote up, because do that again, because it's so we don't want to lose marks when we know our sketch is basically right. There you go. I think we'll get away with that. Use a ruler in the exam, I probably would advise. So that's y equals to minus 2, and it's going for the origin. So that's going to give us our 3 marks for that one. Okay, let's have a look at part C. Part C is really it's more functions, but it doesn't relate to the two sketches directly anyway. Gives us a function here. And says state the range of fx. Now you could do a graph of it, but really we should know that e to the minus 3x is greater than 0 for every value of x. The graph of e to the minus x does this, or e to the minus 3x does that as well, and it goes through 1, so it's always greater than 0. So that must mean that fx has got to be greater than minus 4. Because this bit is greater than 0. So that's our range. Right, let's do part D. F minus 1x. Well, let's let y, because it's difficult to write the algebra of fx. So we've got e to the minus 3x minus 4. Now, basically we can swap the y and x values around and then rearrange. You can do that. Some people swap the y's and x at the end, some people do it at the beginning. I tend to do it straight away. So for the inverse function will be of this type. X is equal to e to the minus 3y minus 4. So it's just a matter of rearranging that. So we've got x plus 4 equals e to the minus 3y. So then we have minus 3y is equal to ln x plus 4. So then we have y equals to minus a third ln x plus 4. With no need to do anything more than that. That's as nice as it can be, really. But we better write it in the notation that we might be expected to make sure we can see it's an inverse. We've not fully defined a function unless we give the domain, but because we have a range here of fx, that's y is greater than minus 4, here the domain of that will be the range of what the original function was, so that's x is greater than minus 4. Don't forget to do that, you will lose marks if you don't. Okay, and then finally part E. Express fg as a polynomial in x. So we've got this other function. Let me tidy this up so I can see everything at the moment. Right, part E, express fg as a polynomial in x. So what we must appreciate here is this means g first. So g into f. So we're going to put this into this. So fg of x. Going to look a bit unwieldy to start with. Minus 3 ln 1 over x plus 2 minus 4. So that equals e to the ln, using the rule of logs, 1 over x plus 2 to the power of minus 3 minus 4. Now the e and ln's cancel each other out, because e of ln, by definition, is like any two inverses. Square rooting of a square just undoes itself. So that just comes with 1 over x plus 2 to the minus 3 minus 4. But of course that's on the bottom, so that's x plus 2 cubed minus 4. Now it does say express it as a polynomial, so I think we're going to have to multiply that out using binomial. That's x cubed plus 3 times by x squared times 2 plus 3 times x times 2 squared plus 2 cubed minus 4. So that comes to x cubed plus 6x squared plus 12x plus 4. Okay, not too bad that question. A lot of marks available. We've got 7, 10, 13, 14 marks and not that long, so it's not too bad. Let's see whether the same goes for the next question. Okay, so it's a vectors question. So that we've got two vectors. I'm going to show that they meet and find where they meet. So this should be bread and butter for most of us, I hope. I'm going to write the two in this way: minus 4 lambda. Just write it as 1 and 5 plus 2 lambda. For one of them, that's line L1, and L2 is R equals to 2 plus 6 mu, and 0 plus 3 mu. So what we do is we just, if they meet, if all of these equations that hold for some value. So if we've got to have 12 plus 5 lambda equals to 2, and minus 4 lambda equals to 2 plus 6 mu, and 5 plus 2 lambda is equal to 3 mu. Right, so if we can find the value for lambda here, and that lambda produces the same value of mu in both of these, then we can show that they meet, and also we can easily sub it back into L1 or L2 to find where they do meet. So solve. Let's number them so we know what we're doing. So solve 1. Then we've got 5 lambda equals to minus 10, lambda equals minus 2. So then looking at 2, solve 2, that gives us that minus 4 plus 8, when I put minus 2 in there, plus 8 is equal to 2 plus 6 mu. So that gives us 6 mu is equal to minus 4 equals to 2, so mu equals to a third. Now we can check 3 to see if this works. Check 3, we've got 5 plus 2 times a third equals to 5 2/3, and no, that's the wrong value I've subbed in, isn't it? 5 plus 2 times minus 2 equals 1, and also if I sub the third into here, 3 times a third equals 1, so they're the same, so they do meet. When lambda equals to minus 2 and mu equals to a third. I'm going to put in this one because it's less to sub in and the numbers are easier. So they meet at 2, because as I say, there's no number to sub in there. 6 times a third for this one. 6 times a third is 2, so that's 4. And then put in mu as a third into this one, we get 2, 4 and 1. They meet at 2, 4, 1. There we go. Right, not too bad either, fairly standard. And this is pretty standard too, because it wants the angle between L1 and L2. And we use the dot product to do that. Yeah, we're going to use the dot product for B. Basically, the dot product of two vectors is equal to the moduli of the two vectors times by cos theta, but we can find the dot product by multiplying the components. There is a proof for it, nice proof for it in the various textbooks. Anyway, cos theta is equal to A dot B over mod A mod B. So we just need to work out A dot B. And it's what I haven't mentioned is it's the direction vectors that we do this for. These two bits are called the direction vectors. So if I call this one A and this one B, so A dot B is equal to 5 times 0, because it's that times that, or minus 4 times 6, sorry, or, not or, and minus 4 times 6, and 3 times 2. So that's minus 24 times plus 6, so that's minus 18. And then we need to find the moduli of each of these. The moduli of A is 5 squared plus 4 squared plus 2 squared. Just ignoring any negatives because they just give a direction. So 5 squared plus 4 squared plus 3 squared, the square root of that. So that's 25 plus 16, so that's 3145. And the mod of b is equal to 0 squared plus 6 squared plus 3 squared. So that's 36 plus 9, so that's also the square root of 5. So we have cos theta is equal to minus 18 over the square root of 45, the square root of 45. So that's minus 18 over 45, which is minus 0.4. So if I do the inverse cos of that, so I've got inverse cos or arc cos of minus 0.4. When I do that, I get 113.6. But of course, we want the acute angle. Really, when we're talking about lines, the direction vector is kind of not what we're too interested in, really. But the only reason why it's come out as a obtuse angle is because of the direction, the way the direction vector is going. But if we're actually only interested in the acute angle, we want 180 minus that. So the acute angle is equal to 180 minus 113.6. So that equals to 66.4 degrees. Okay, so that's part C done. Part D, often with the vectors questions, is the challenging bit, and I suspect it will be here too. But of course we've got to do the more straightforward part C, just one mark so that this lies on L1. We just need to come up with the appropriate value of lambda. Well, we need to get 7 for the top, which we can see we'll get if we make lambda equals to minus 1. So you just say when lambda equals minus 1, R equals to 12 minus 4, 5, plus minus 1 times 5 minus 4, 2, and we can see that that gives us 703, so that lies on the line. So B lies on the line. Right, so part D, as I say, is going to be the challenging bit. Let's draw our two lines. A diagram is almost always necessary, I think, if not at the beginning, towards the end of these questions. Right, so let's write L1 here, L2, and we've got point B is on L1, and that's got coordinate 703. And we know the coordinate where they meet, that's the coordinate of intersection, that's point A. We know that as well is the, where was it now? Oh, I've lost it. Where is it? Yeah, the 2, 4, 1 here. So we know those 2 points, so that's important. And it says find the shortest distance from B to the line L2. So the shortest distance will be perpendicular. Let's draw this in red. So the shortest distance will be perpendicular to this. There. Okay. Well, we also know this angle, because this angle here is 66.4. And we can easily work out the length AB. So it's once we've got our diagram, we'll just use normal SOHCAHTOA geometry. Let's call this D, this distance, the shortest distance. And we can just do it. So let's just go back to blue. Okay, so AB, the distance AB is equal to the difference in the x coordinates of the 2 and 5, so that's 5 squared, plus the difference in the x coordinates here, which is 4 squared, plus the difference in the y coordinates there, that's 2 squared. So that's 25 plus 16, that's 31, that's square root of 45. Okay, so we've got square root of 45 is that. So now we can just do normal SOHCAHTOA on the triangle here. So that gives us shortest distance D is equal to square root of 45 and it's sine 66.4. Use the stored value you would have had from before, just in case we get any rounded errors, and that comes to 6.15. Okay, that's the easiest way of doing this question when we know the point is on the line and we've got the angle between that and the line is easier. So there are other ways of doing it, but it's definitely quicker to do it that way in this circumstance. Okay, one question to go, and then we're done. Okay, so it's a parametric equation to finish. This will be on C4 for home students, and home students need to be thankful that they don't have these papers, because although the questions don't seem to be much harder, it is more of a slog to get through it. I've noticed that whilst doing this series of questions. So, yeah, it would be on C4, pretty standard, I think, relatively. So we've got to find dy by dx in terms of t. So let's find dy by dt, which is differentiating sine gives you cos, so that's 2 cos t. Find dx by dt. Differentiating cos gives you minus sine, but don't forget to times by the 2. So that's minus 12 sine 2t. So now dy by dx is equal to dy by dt over dx by dt. So that's equal to 2 cos t over minus 12 sine 2t. We're obviously going to need to expand to bottom. I'm also going to deal with the 2 and the minus 12 at this point. So we've got 1 and minus, we've got cos t on top. We've got minus 6, but the sine 2t is 2 sine t cos t. Okay, and the cos t cancels. Okay, so that gives us minus 1 over minus 12 sine t which is minus 1 over 12 cosec t. There you go, that's that part A done. Right, part B, let's do it over here. Part B, find the equation for the normal at C when t equals to pi by 3. So we're going to do x and the y, and it should be pretty standard 6 marks, I would think. For this stage in the paper, it doesn't feel too bad. Maybe there's something nasty to come. I haven't looked at it yet. Anyway, so we're going to put t equals to pi by 3 in there. So when t equals to pi by 3, x is equal to 6 cos 2 pi by 3, which is equal to minus 3. And also y equals 2 sine pi by 3, and that equals to, because sine pi by 3 is the square root of 3 over 2, so that equals to the square root of 3. Now dy by dx, or dy by dx is equal to minus 1 over 12 cosec pi by 3. Now that equals to, that's 1 over sine pi by 3. So that's minus 1 over 12. Now sine pi by 3 is equal to the square root of 3 over 2. So that's 2 over the square root of 3. So that equals to minus 1 over 6 the square root of 3. I'm not going to bother rationalising because we want the normal. So the gradient of the normal is 6 the square root of 3 because it's minus the reciprocal of that. Yeah, find the reciprocal of that and you'll get minus 1 over, we'll get 6 minus 6 3 and we change the sign. So that's the gradient. So now I'm going to use, I know other people use other ways, but I'm going to use y minus y1 x minus x1 and y minus the y value, which is square root of 3, is equal to 6 the square root of 3 x plus 3, and because it wants it in y equals mx plus c form, I'm going to multiply out, so that's y equals to 6 the square root of 3x plus 18 the square root of 3 plus another square root of 3, so that makes it 19 the square root of 3. Okay, so that's part B done. Now, let's see if part C has got anything nasty about it. We're nearly done here now, just 4 marks out of the 120 to go. We're told the Cartesian equation can be written in the form x is equal to the function of y. Find fy, where fy is a polynomial in y and k is a constant. Find fy and state the range. Okay. So normally with this kind of thing, we're using identities. We want to basically shove the value of y into here, and we can see that immediately x is equal to 6. If I express that in terms of sine, it will be much easier. That's 1 minus 2 sine squared t. Okay, so now I can shove, but I know that that sine t equals y over 2. So I've got x is equal to 6 times 1 minus 2 y over 2 squared. So that gives me x is equal to 6 times 1 minus 2y squared over 4. So that gives me x is equal to 6 minus 3y squared. Okay, so not terribly interesting parametric equation really, it's just a parabola. After all that, I wonder why anyone would do this, but anyway, some of I like the ones which do loops and all that kind of thing, but this one's not particularly interesting, but who cares, we're at the end of the paper nearly. And it says state the value of k. Well, if we put pi by 2 in there, we'll get the value 1, and if we put minus pi by 2 in there, we'll get the value minus 1. So the range, the value of k, so we can say that y is greater than minus 2 and less than 2 is the range of the function. So k equals to 2 in other words. Okay, so that's it. 30 minutes done. I think I've spent a couple of hours on all of these questions, but probably ought to learn not to waffle on too much. Hope it was fine for you anyway. Bye.